In this video, we're going to be looking at this problem, logger rate limiter. We're asked to design a logger data structure that receives a stream of messages along with their timestamps. Each unique message should be printed at most every 10 seconds. So this means that if a message is printed at time t, we'll prevent it from printing identical messages until t plus 10. And all the messages will come in chronological order. So let's take a look at the example. So first at t equals 1, we receive foo. So since we obviously haven't seen any messages yet, we print it, so we return true. At t equals 2, we receive bar. Same thing, return true. At t equals 3, we receive foo again, but it hasn't been at least 10 seconds since the last time we saw foo, which was at t equals 1. So we don't print it and we return false. And so on. So try the rest of the examples on your own so that you can get a better feel for the behavior of the system. Let's break this question down. So there's multiple ways of implementing this logger, each with their own legitimate trade-offs that you can reason with later on. But let's start off with the first design. So the input looks something like this. It's a stream of messages. So the first thing that we need to do is keep track of which messages, foo, bar, we've already seen. Then we can associate them with their timestamp. And every time we encounter a new message, the first thing that we want to do is check if we've seen the message before. So if yes, we check if we're within the 10 seconds since the last time we saw it. So if yes here, we return false. And if no, then we want to update the message's associate timestamp to be the current timestamp, and we return true. So in terms of implementation, a hash map is exactly what we're looking for here, where the keys are going to be the messages and the values are going to be the timestamp. So let's see this in action. Let's first initialize an empty hash map. So first we see foo at time 1. So since we haven't seen foo before, we add this to the hash map and return true. Then we see bar at time 2. So same thing, since we haven't seen bar before, we add this to the hash map and return true. Then we see foo at time 3, but it hasn't been 10 seconds since the last time we saw foo, which was at 1, so we return false. Same thing with bar at time 8, and foo at time 10, since it's been 10 minus 1, which is only 9 seconds so far. And then we see foo at time 11, so it has been 10 seconds, so we update foo to be 11, and we return true. So for time complexity, we're getting 01. This is because inserting the messages and checking the messages in the hash map are all O1 operations. But in terms of space, the size of the hash map will grow with the number of unique messages. So it's actually OM, where M is the number of unique messages. So now the impact of this would really depend on the real world implications. So if this logger was expected only to log a small number of unique messages, this is great. But if it were to be logging any arbitrary message string, the memory usage would essentially never stop growing. So this is something to keep in mind, and it's important to explain this trade-off during an actual interview. So now we have a working solution here. Let's implement this in Java. Let's start off by creating that map. Be a map of string to integers since it's messages to timestamps. Going to initialize it here to be a hash map. So first thing is, if the map does not contain the message, we know that we can return true here, since we have not yet seen the message at all. And then Also, we have the case where the timestamp minus the message's current timestamp is greater or equal to 10. So at least 10 seconds has elapsed. So in this case, we also return true. But then also in addition, we want to update the message's timestamp to be the current timestamp here. And then as we said, all other cases we return false. All right, let's run this. And cool, it works. Let's look at a different design. The issue that we saw in the previous design was that even though it had constant time, it had OM space, which could grow arbitrarily large. Another way of thinking about this question is that at any given point in time, all we really care about are the messages that have not yet currently been invalidated by the 10-second time limit. What if instead we use something like a sliding window? Let's use a queue. So this queue represents a sliding window of all the messages that we have seen that have not yet been invalidated. Every time we encounter a new message, which is at timestamp t, we can remove from the queue any messages with expired timestamps, that is, whose timestamps are less than t minus 10. But then how would we know which messages are still in the queue without needing to traverse through it, of course? Well, we could use a hash set. And the hash set would keep track of all the messages still in the queue, which means that every time we remove an item from the queue, we also remove its corresponding message from the hash set. So let's see this in action. Hopefully this will clarify things instead of just talking about it. So let's initialize an empty queue and an empty hash set. So first we see foo at time 1. So since there's no items to remove before the time minus 10 seconds just yet, and also hash set does not contain foo, let's add 1 foo to the queue. And then we're also going to add foo to the hash set. And we return true here. Next we see bar at time 2. So same thing, let's add 2 bar to the queue. And we're also going to add bar to the hash set, and we return true. So next time we see foo at time 3, well again, there's no timestamps to remove before time minus 10 seconds yet, but the hash set does indeed contain foo. So we know that foo is still a valid message. So therefore we return false here. Next time we see bar at time 8, it's the same thing. There aren't any timestamps to remove before time minus 10 yet. And since bar is in the hash set, we know that bar is still a valid message. We return false here as well. Same thing with foo at time 10, we return false. And now this is where it gets interesting. So we see foo at time 11. So let's first remove everything in the queue before the time minus 10 seconds, 11 minus 10, which is 1 second. So the only thing we can remove right now is 1 foo. But as we said, as we remove it from the queue, we also remove its corresponding message, or foo, from the hash set. Now at this point, since hash set does not contain foo, we know to add 11 foo to the queue and add foo to the hash set. And we return true here. Great, so we have a solution here. So in terms of time complexity, well, in the worst case, we have to remove all the items in the queue if at time t, t minus 10 invalidates everything in the queue. So removing an item from the queue is O1, removing corresponding message from the set is also O1, but with n items, this is On in the worst case, n being the size of the queue. In terms of space, well, in the worst case, we keep n items in the queue and n items in the set if all the messages are unique. So the space complexity is also On. Okay, great. Now let's implement this in Java. Let's start off by creating a helper class called item, which is going to hold that timestamp message pair that we mentioned. Then we have the queue. We also have the set. And then in the constructor, we're going to initialize a new queue as a linked list, and the set as a new hash set. So while the queue is not empty, and the queue's first item's timestamp is less than that t minus 10, we're going to be removing items from the queue. So we're going to do item equals queue.pull. And then as we said, we're also going to be removing that item's corresponding message from the hash set. So now at this point, if the hash set still contains the message, we know that that message has not yet been invalidated, which means that we can return false here. And then otherwise, well, this means that we need to add that pair to the queue. So let's add a new item, timestamp message, and then we're going to add its corresponding message to the hash set. And we return true here. All right, let's run this. Great, and you'll see that it works. And that's how you solve the logger rate limiter problem.